So this is a project called Demistiphy that Sergey and I have been working on. The idea is that at layer 1, there are all sorts of weird effects that occur when packets are misinterpreted. The first of these that we found was packet in packet, for which we won the Pony Award a few years back. But there are more of them, and as packet in packet defenses are built, you need to identify strange behaviors at layer 1 in order to bypass those defenses. This is also handy for active fingerprinting because it teaches you ways to, it teaches you ways to mispresent, or to mistransmit a packet, to violate the protocol in a way in which some receivers can still understand you, but others cannot. So you can transmit a packet that, because of its phi layer properties, can be received only by a particular brand of chip or by a particular software stack. So this is built upon Wright's principle, which is that things don't get better until you have attacked tools to demonstrate the problems. In our case, the fun stuff that you can do at the phi layer implies that the phi layer itself is completely untrusted, and that the upper layers sort of depend upon the lower layers all the way down, not because at the bottom it becomes trustworthy, but because at the bottom it becomes relatively unknown. And you have very few people working on the security of the phi layer, or where they are, they're working with cryptography or with special defenses, and not with unique attacks against legacy systems. This is an 802.15.4 packet. It has a number of fields. If you extend it outward, you have all of these. If you extend it further, it gets even worse, with fields cross-referencing each other. No one who actually uses this protocol understands what every one of these fields does. So to play with this, is, a number of different hardware devices can handle this. We've been using the Atmel RZ USB sticks and the T-Mote TLO-SPI. The Freaktuino Chibi is also in the lab. And then there are commercial analyzers that do it. But we're doing all of this research without software-defined radios. They're terribly handy for understanding what's going on. But at the same time, they're not the sort of devices that you would be finding in the field. And they're too expensive to deploy in large experiments. A software-defined radio can receive packets in the raw and then parse it later. It's great for seeing what you're doing. But it sort of abstracts you away from what's going on at the physical layer, so you don't really pay attention to how the parser is working. Toward that end, we've decided to stick to the default hardware-based implementations, and we've now got our own board, the AP mode. Over on the left end, you will see, is there a way to dim the front light without the back, or am I getting greedy?
Shut them off.
Okay. So over here on the left, you'll see the ChipCon 2420. This is a radio, but it is a digital radio chip that allows for packets to be received and sent, but it does not have a Turing machine inside of it. So you can only program it by setting settings into special function registers. You can't actually write software into it, and it runs no software of its own. The software runs inside of this chip, the MSP430 F2618. This is a 16-bit RISC chip that's vaguely like the PDP-11, but mostly for marketing reasons. And then over here on the right, as is cut off in the photograph, there's a USB port for talking to a host computer. So the fairy tale of the way that the phi layer works is that you have this magic frame, and it gets shoved through the air, and then you have your link layer frame, and everything is good. And this is sort of missing the step in the middle, right? You know that the packet is transmitted, you know that it's received, but exactly what happens is skipped over because you as the application designer or as the firmware developer can just ignore this because the radio chip takes care of it for you. Ages ago, this wasn't true. It used to be that you would have to write software to do the decoding. So you might get an audio signal and you'd have to pull modem noise out of it. And so that's the part that we're trying to cover here, like exactly what happens to the packet as it's in the air and exactly what happens when packets are misreceived. What happens if you're one channel off? What happens if you're a little bit late or if there's a frame collision? How can you get the packet itself to turn back into the pumpkin?
So if I may jump
Yes.
in at this point. It's parsers all the way down. So the waveform is parsed by several layers of simple machines in the physical layer. This I find the most fascinating aspect of this. So for example, here you see the frame parsed into frame control, sequence number, address info, payload, and the rest of them. And somehow the start of the frame is extracted from the waveform. What does it? A simple machine. Then you have to know when it stops, right? Again, noise doesn't just magically become a frame. A simple machine matches the beginning. It doesn't just magically become noise at the end. A simple machine takes care of the matching the end as well. Well, it doesn't quite match it. Instead, it goes on the information that was transmitted at the beginning, the length of the frame. But it's those simple machines that are the target, because you expect what you expect of them is consistent parsing that all your upper layers will depend on. And are they complex enough to actually provide that? And the answer is
So there are two ways in general to implement this magic. The easiest way to implement the magic is that at the beginning, on the left, at the very beginning of the packet, you have a start of frame marker. This is a symbol that tells the receiver where the packet begins. And then you have a length. And then you just tick off the length number of bytes by having a counter that counts downward to 0, running until the end of the packet. And then you don't actually mark the end of the packet physically. It's just that the counter expires. And this is how 802.15.4 does it. This is how, in one way of thinking, Wi-Fi does it. Although Wi-Fi has a bit of a complication on top. But there's another way to do it, which is that you can have an out-of-code sequence that explicitly marks the beginning and the end. This is how Ethernet works. This is how PCI Express works. So in both Ethernet and PCI Express, your packets themselves have no length at the PHY layer. There's a beginning and there's an end, but there's no length field that tells you how long the packet will be. And that's because it's implied by a beginning and an end marker. And it's only the upper layer packets that have length fields. And because this is skipped over, it becomes a piece that we can attack. And because it's a parser, it's not that hard to figure out how to begin looking for bugs in the parser. The way that this directly works on 802.15.4, we've arranged this lecture as a series of lies about how things work, and then we'll sort of back up and point out how we misrepresented things. But as I'm lying to you now, it's just by sitting at a higher layer of abstraction than I might be. So it's like, lying to children is an honest profession. It's teaching. So here you have the preamble. These are the zeros. The zeros symbol in 802.15.4 is, it still wiggles around a bit. It's actually 32 ones and zeros at the lower layer. So these preambles, these 0 bytes, are used so that the receiver knows what bit timing the transmitter is using. Otherwise, the clock drift would be so severe that by the end of the packet, the receiver would not know where a bit begins and ends. And in drifting off, it would begin to make mistakes in identifying those bits. A7 is the sync field, or the start of frame delimiter field. This is the single most important part of the packet. This is how the receiver knows where the packet begins. Following that, you have a length field as part of the body. In this case, the length field is 0f. So you have 15 bytes that follow of data. And then at the end, there's a checksum, which is CRC16. In And you can sort of imagine how collisions would work. But we'll get back to that in a minute. Now, when this is received, it's the ChipCon 2420 that actually handles the reception, because the microcontroller can't be bothered with all of the background noise. It's too much parsing to do, and it would keep this chip awake and waste too much power. So in order to save power, and in order to save processing capability, the ChipCon 2420 looks for the start of frame marker in hardware. It has a couple of simple machines inside of it, none of which are Turing complete, which take the background noise, constantly resynchronize against it as if it were a preamble in order to adjust its bit timing. And then at the same time, it looks for 00A7. That's the end of the preamble and the beginning of the start of frame delimiter to mark where the packet begins. And as soon as it sees that, it snaps into a reception mode and begins loading the receive buffer with all of the bytes that follow. Sergey?
So this is the view of the packet below the link layer. So preamble sequence, start of frame delimiter, and then the frame length. You will not see them in Wireshark. They exist explicitly for the consumption of the chip, and the radio chip will not give them to you, as it were. However, what you can do is set the length of the preamble, and you can also set the start of frame delimiter, which turns out to be extremely useful.
So the preamble itself is used in order to allow the transmitter and the receiver to agree on timing. In today's world, we all have watches, and they all synchronize by the towers, and they're all within 2 or 3 minutes of each other. But it used to be that keeping consistent time was a terribly difficult problem. So the invention of the spring-loaded clock that could function on a rocking ship in a way that a grandfather clock cannot was a really big deal, because that would allow the ship to know what time it was in order to figure out its longitude. The longer the ship would stay at sea, the further its clock would drift from its setting on land. And in today's radio world, you have the same problem. You can get high precision radio signals, high precision timing signals from an atomic clock or from GPS. But the data is coming across very, very fast. So as these bits and subsymbols called chips are swinging at the receiver has to know at exactly which time to sample the signal to determine what the incoming bit is. And the way that they agree on this is that the transmitter and the receiver have separate clocks. And the receiver has a phased lock loop that it trains on the preamble of the transmitter in order to know how wide the bits will be. If you're at low data rates, like 1200 baud audio modem, there's no need to do this, because you can consistently match that with a quartz crystal. But at the higher speeds, you can't do that. You also have variances from temperature.
Clocks drift, right? From the point of view of wireless, we're all at sea. Of course, what you make your bits and any transmission out of is the sine wave. It's the universal building block of everything, and of course you have the oscillator to produce it for you, and then you modulate it. This is the bare naked sine wave. This is the amplitude modulated sine wave. This is the frequency modulated sine wave. But in order to actually agree on what the sine wave is that you're modifying that way, you need synchronized clocks, but clocks drift.
You also need some time to train the automatic gain controller. So inside of the receiving radio, there are amplifiers that can be turned up and turned down. The preamble gives it enough time to adjust that amplifier to be correctly set to the strength of the incoming signal. This was used as a copy protection measure for audio cassettes on the Apple II and on the Commodore 64. At the time, you would get your software on an audio cassette, and then it would have modem noises on it that your computer would decode. The problem was that dual cassette decks became available at the same time. So how do you keep one of your customers from copying the audio cassette in order to give the game to a friend of his? And the trick that they used was that they'd have a screech of very loud noise just before the start of frame delimiter in one of the modem packets. And then if you play it into an Apple II or a Commodore, which does not have automatic gain control, then it works fine because it's too loud during the meaningless part, and then the volume drops for the regular part, and you can still hear the packet. But if you copy it in a dual cassette deck, the cassette deck thinks that you're copying a very loud death metal tape, so it adjusts the levels to match, and then the quiet beginning of the packet becomes too quiet to hear, and the beginning gets missed, so the game doesn't work.
So then, how much of this preamble is needed? How good is your chip? How tolerant is your chip to synchronizing on this much? Luckily, we do have a register for setting how many zeros we send as a radio. But what about the receiver? Receivers differ. Some receivers might be able to synchronize on just one of those bytes. Some would need more. This really depends on, everything, including temperature, because the clock depends on temperature.
Now, so this is a rather odd preamble in that it's zeros. For competing chips, most of which are frequency shift keyed, which means that the transmitter transmits just a little bit lower on the frequency for a 0 and a little bit higher for a 1, you'll see a different pattern. You'll see 5s and A's. Why is that? Right, so you want to alternate between the two signals so that the receiver knows how far the transmitter's deviation is, how far the 1 is from the 0. Here, it looks like they're not doing it because they're only sending zeros across. But as you'll see in a bit, each one of the nibbles in this message is actually a sequence of 32 ones and zeros, which provide enough spread. So by changing the number of preambles that we sent, we were able to selectively transmit to only certain devices in order to transmit just to the T-Mote or just to the T-Mote and the Zigduino while cutting out the RZ USB stick. And these use 3 different radio chips. So the T-Mote uses the ChipCon 2420. The Zigduino uses an older Atmel standalone radio chip. And the RZ USB stick uses a more modern Atmel chip. And you can see that these have drastically different tolerances for a shortened preamble. The CC2420 matches the final 2 nibbles of the preamble as if it were a start of frame delimiter in order to reduce the number of false positive packets that it receives. If you leave any of these radios alone in a room with checksumming disabled, they will begin to give you packets even if there's no transmitter nearby, because they misidentify Wi-Fi traffic as being their own traffic. The ChipCon 2420 does this the most often because it's matching on the shortest sequence. It matches on just 4 nibbles, 00A7. The RZ USB stick, even with checksumming disabled, shows very few because it's matching on almost the complete preamble as part of the start of frame delimiter.
There has to be a proper naval joke for this, since we're all at sea.
Now, the next part is the start of frame delimiter. From the radio's perspective, all background noise has to be matched to some symbol, even if that symbol is wrong. So the symbol matcher is constantly spitting out what it thinks the current symbol is, and then at some point, its output is A7, preceded by a couple of zeros. And it's at that point that the packet begins to be received, and then the packet symbols begin to be shuffled into a frame buffer. And this buffer is what the receiving microcontroller will read. It's a common bug in updating the microcontroller on one of these boards, that the packets begin to become corrupted. And the reason why is that the older chips would default to 3 megahertz, and the new chips default to 16 megahertz, which means that the new microcontrollers can read the packet out of the buffer faster than the buffer is populated by the radio. So during that time, the copy routine passes the end of the packet. Now, as I said before, this starter frame delimiter isn't always in the symbol set. In 802.15.4, it is. So 00A7 marks the very beginning. This is Zigbee. In 802.11b, it sort of is. The symbol set changes in the middle of an 11b packet. So when you send a 12 megabit 11b packet, the header begins at 1 megabit, then jumps up to 2, and then from there jumps up to 12. But at the lower speeds, the starter frame marker is a part of the packet itself.
So this is fascinating. In the actual preamble, you have the preamble and the SOD, and then the beginning of the frame. You have a clue whether you should switch to a different modulation scheme halfway or not. This is halfway through the packet. This is why running B on the same network as G is really interesting, because your B cards would not recognize G packets. So they would start speaking loudly and obnoxiously in the middle of a much more brittle G packet, which happens at the faster rate. So that they don't do this, you send, before each packet, a request to send frame, RTS to self. So that in B, so that B clients know that a frame transmission is going on and the bandwidth is reserved for so many microseconds. Which is why bringing a B card to a G party is not a nice thing to do. It spoils the service for everyone.
This is also why you will often see the length field of a Wi-Fi packet described in milliseconds instead of in bytes, because the outermost frame is designed to be received by a radio that might not speak the inner frame's protocol. So it makes sense that the receiver wouldn't know how long a number of bytes would take. But not all protocols do this. PCI Express has a very strange error correction code. Every byte is expanded to 10 bits. In a 5-bit portion, no, every byte is sent as 12 bits. So your 5 bits become 8 bits, and then the remaining 3 bits become 4 bits. And this provides error detection and error correction for all of the 256 valid bytes. But there are also extra regions in this code that would be corrected inside of a frame, but are terribly rare to reach. So these serve dual purpose, in that you can never create these on the inside of the packet, but they mark the beginning and the end. So there are special control sequence codes, one of which is a start of frame marker, one of which is an end of frame marker. One of them is a no-op that actually means nothing, but will get stuffed into the packet whenever the transmitter needs a little bit more time. And also at regular intervals, so that the receiver can cut them out whenever it needs a little bit more time. And that way, if the PCI Express card and the PCI Express controller are running at different clock rates, they don't collide by not being able to populate their memory fast enough. And this saves them from having to have twice the memory speed of their bus speed.
Allow me to demonstrate.
Yeah, same thing. Except I'm not very good at tearing those out. So because the start of frame marker uses the same symbol set as the body of the packet, we came up with an attack called the packet-in-packet attack. So just looking at the hex in the top row for now, that's a Zigbee packet. If the end of that packet gets damaged, then the checksum, except by an act of God, will be wrong. And when the checksum is wrong, the packet will get dropped. And it's dropped explicitly. So the receiving radio knows that a packet began. It had the packet in its buffer. And then at the end, the checksum was wrong, so it decided to flush the buffer and forget about the packet. But if the A7 gets damaged, then the packet gets dropped implicitly, in that the packet goes past the radio, but the radio never knows that the packet ever began. So instead of marking the checksum as bad and then dropping the packet, it will just sort of forget about it. It doesn't affect any of the error statistics. It doesn't show up as a dropped packet on the host operating system. It's almost as if it never happened. But this creates a lovely little state where in the middle of the frame, it's listening to data, to layer 7 data that the attacker controls, thinking that it's background noise waiting for a packet to begin. So if we knock out this A7, then the receiver that's going along, instead of stopping at this A7 here, looking at my shadow, it will instead stop at this A7 here, which is part of the body as far as the real packet is concerned. It becomes the sync field or the start of frame delimiter as far as the inner packet is concerned. So in this way, we can inject a layer 1 frame in the raw, given control of only layer 7 data. So I can email a Wi-Fi beacon. And it doesn't matter that a Wi-Fi beacon can't be encoded in TCP/IP. It doesn't matter that it can't be encoded in email. I can send it over UDP if I like. And as long as I can get it relayed over the air, and as long as I know what the radio symbols will be produced by it on the air, I can then adjust those symbols to produce the sequence of data that I like.
Actually, there's a problem with emailing it, which is that there are still mail transfer agents out there that will strip the top bit when you try to send it A7 through them.
Yeah, we've not come up with a 7-bit clean version, but but all email is HTTPS anyways these days. Whatever. So so this is an expanded view of a complete injection, and you'll note that the leftmost column describes what the packet should be. This is the packet if there's no damage. The rightmost column shows what the packet looks like if the synchronization field is missed. Now, if you think of this as like the probability of that one symbol and no others being damaged by a random symbol error, this is terribly unlikely to work. Like you could retransmit it enough for it to work, but the odds are against you. So the way that this works in the real world is not that there's a random symbol error, which would be the appropriate way to model it if you had a clean radio channel with no interference, or you were transmitting over a cable. What happens is that there's a frame collision, which is how the 2.4 gigahertz spectrum suffers daily. So this laptop does Wi-Fi, but it also does Bluetooth. Wi-Fi has a method of getting through interference, which is that it politely requests for use of the channel, and then it uses it. Bluetooth has a method for dealing with interference, which is that it channel hops so quickly that any interference will only hit it on one of its channels. But this means that Wi-Fi is taking use of a channel for a long time, blotting out all of the Bluetooth traffic that tries to go across in that channel. And Bluetooth is hopping over every channel, transmitting garbage and interfering with the middle of Wi-Fi packets, and they collide with each other. For a short packet, like a Zigbee packet, like 802.15.4, the way that a collision will work is that either your packet is completely obliterated, which is of no use to us, or the end is damaged, which is of no use to us, or the beginning is damaged, which is the exact case that we're looking for. And we've measured in busy Wi-Fi environments that we can get up to 1 out of every 20 packets injected successfully. So you can send a 5-frame without a radio if you control the layer 7 data and you know what it will look like at layer 1, and there's radio noise. Now this part about knowing what the application layer bytes will look like at layer 1 is trivial for Zigbee because they're not encrypted and they're not scrambled. Well, we're assuming that there's no encryption. Encryption breaks this. We have a paper on this for which we won a Pony Award at Black Hat in 2011.
Turning pumpkins into ponies.
Yes. And the title of it is Orson Welles' In-Band Signaling Attacks Against Modern Radio. In 1938, Orson Welles did his famous War of the Worlds broadcast. And he uses the exact same trick that we use. War of the Worlds begins with a 2-minute, 38-second introduction that explains that it's a Halloween prank. But it began 7 minutes before the hour. So when people tuned into this show, they tuned in late. And they tuned in during the 35-minute long first act, which is done entirely in character without a single word out of character, a single commercial break, a single announcement, or anything to tell you that it's fiction.
Except the commercial breaks were...
Well, while there are no commercial breaks, there is a fake commercial show, Ricky Raquello's Orchestra on the Air, that keeps getting interrupted by fraudulent news broadcasts, government announcements. The first act ends with the New Jersey militia nationalizing the central broadcasting system, which then gets blown up by aliens, and a lone ham radio operator ends the first act by asking on the air if anyone is left alive. And he does this same exact trick that we do, in that his fraudulent station announcements assume that the listener will enter the broadcast late. In his case, it was because of channel hopping. In our case, it's because of a frame collision. But in both cases, the recipient tunes in late, hears fraudulent announcements that identify what the station broadcast is, and then the listeners get confused. When this was translated to Spanish and performed in Peru, it was so effective that the radio station was burned to the ground. 6 people died, and the director had to flee to Uruguay. And the reason why there was that the locals are listening to it, and they're not stupid, right? So they're listening to the radio, and the radio tells them that aliens are invading. And they think this is ridiculous. If aliens were really invading, we would see the army rolling trucks up Main Street. The problem was that the army heard the same broadcast and figured it couldn't hurt to send some trucks to the Sanchez farm to see if aliens were really landing. So I told you that the symbols were nibbles wide, that 0 was 32 chips long, but I didn't explain what those chips were. So this is the complete set of chips for 802.15.4. This comes from a papercraft game that we made. So, each one of these, you have like symbols for 0, symbols for 1, all the way up to 7, and again for 8 to F. And these actually form 2 different rings. So if you, which way does it go? Yeah, if you take the 8 and you right shift it by 4 chips, that's these ones and zeros as opposed to the higher layer bits. If you right shift it by 4 chips, you get 9. And if you take 9 and you right shift it by 4 chips, you get A. And the same happens in the other sequence. So 0 right shifted becomes a 1, 1 right shifted becomes a 2. So these exist for error correction. The idea is that when you have such a low-powered radio, you can do a trade-off between the number of symbols that you send and how the amount of information that you send and how tolerant you are to interference and to errors. So the receiving device grabs these 32 chips and then finds the nearest match by Hamming distance. It is to say the valid number in the set with as few bit flips as possible. So some of these bits arrived flipped, but it doesn't matter because the Hamming distances of these 32 chip codes are so far from each other. Like the distance between these two is 16. All of them are more than 13. So if up to 10 of the bits flip, you can still accurately find the closest match. And this is entirely transparent to all layers above. So even though this set of symbols is included in the radio datasheet, you as the developer never have to use these for anything. Now, earlier I mentioned the packet-in-packet exploit, where I can send a valid frame in layer 7 by saying 00A7, valid length, body, and checksum. There was a guy at Wireless Days in 2012 who, as a defense for this, thought that he could just take the radio packet driver and have it escape any sequence of 00A7. So what I did was I abused the error correction code. So what I'm trying to do now is to not inject a perfectly valid frame, but instead inject something that at layer 1 looks close enough to a valid frame that the receiver doesn't care about the difference. So I built the papercraft game that I showed you the picture of earlier, and I shifted the things around on paper until I saw the 2 rings. And as you go down any one of these columns, all of the bits are the same. It might be easier to think about this in hexadecimal than in binary. So you see that these all have the same number. It's just that to get to the next item in the sequence, you take the last nibble and you move it to the far left. So this B goes over here, this 7 goes over there, this 7 goes over there, this 0 goes over there, and so on. And these 2 rings are not connected. So what we're doing here is we're left shifting by 1/8 of a nibble, because this whole sequence represents 1 nibble of data. So this allows us to trick a receiver into receiving a frame that was never sent. And the way that we do this is we shift it off by a little. So the preamble is all zeros, and I need to get that through. But that can get escaped by the radio driver. So what I do instead is I send all 1s. And in this entire sequence, only the very last 4 chips will be wrong. So this E matches that E, this E matches that E. Only at the borders between non-repeating values does any of the data come off wrong. So instead of sending a bunch of zeros in an A7, I can send a bunch of 1s and a B0. And you'll note that in the symbols, this D does not match that A7. Sorry, this D does not match the 7. But the 0 matches the 0, the 6 matches the 6, the 9 matches the 9, the C matches the C, the 8 matches the 8. For the entire sequence, everything but the tail end is correct. And that tail end, at worst case, if every bit is wrong, produces a Hamming distance of 4. And remember, the legitimate values have Hamming distances of like 13 to 16 between each other. So I can actually abuse the error correcting feature of this radio to let me smuggle through a packet-in-packet attack despite a defense that's trying to escape that sequence out.
So, observe. All of those boundaries, I mean, we make things easy for ourselves by writing packet contents in symbols, or more precisely, nibbles. But the boundaries between those nibbles do not exist. They're nowhere on the air. The waveform, as decoded by the ChipCon 2420 chip, consists of a stream of chips. There is nothing to separate the chips of one nibble from the chips of another nibble. There is nothing to separate the bytes from each other. They are just artifacts of parsing, because this is exactly what the digital radio chip does to this stream. It extracts boundaries out of it. Everything else in the stack depends on those boundaries. So now you have the situation, if you detect those boundaries, if you parse those boundaries out incorrectly, the rest of your parsing can be controlled by adversary, who, by the way, will borrow your error correction. This is, this is the coolness of an exploit is how much of the receiving system you can borrow, and on how deep a level. I don't know a way to go deeper than that.
So your radio can receive frames that share no frames with the data that was transmitted. In that if you have a software firewall that's trying to prevent these injection strings from getting out, it won't work to do all of this at the layer of abstraction that the packet is received at, because the frames themselves get shifted in between. And it being off by 1/8 of a nibble in time is no problem at all, because the receiver is used to trying to figure out where the packet begins and with what time alignment the packet begins.
So it's very important, right? You can't prevent badness by controlling what goes out. Because the badness that it causes on your system is in the receiving process. It's in the parsing process. You cannot possibly correct that by controlling what you send out. What do we call such a security mode? We call it PEL.
So you have different types of modulation, and you can also play between these types of modulation by controlling a packet in one style and then using that to leak information in another style. So the easiest one is on-off keying, which is kind of like AM. This is what your garage door opener will use. The idea is that to mark a 1, you turn the carrier wave on. To mark a 0, you turn the carrier wave off. And then you receive it kind of like AM, or kind of like you'd receive Morse code, in that you tune AM just a little bit off and it produces an audio noise. Frequency shift keying is kind of like FM, in that you transmit one of 2 frequencies, or sometimes 4 frequencies, and the bit is indicated by whether you're a little bit beneath or a little bit above the center frequency. And then you have phase shift keying, which is kind of like phase shift keying. The idea is that you invert the carrier wave in order to mark the bit, and then the receiver compares that to a reference that's been trained on your carrier wave to see where the flips are. This is an on-off keyed message that was transmitted from Philadelphia. So in this case, it's Morse code. And you can tell that it's machine-generated Morse code because the dits and the das are almost exactly the same length as each other. And the spacing between letters is almost exactly the same as each other. So the first letter is dit da da, that's a W. The second letter is dit 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 da da, that's a 3. And then the rest carries on to decode the entire message. So the radio call sign of this transmitter is W3CCP/B. The other lines of this give the map coordinates for where the transmitter is. And then this beacon comes out over a shortwave frequency that will sometimes ricochet off of the atmosphere. So by listening for these beacons, users can tell where the atmosphere is bouncing for them. Now, suppose that you man in the middle an SSL session, but you don't know the key. This might happen if I am in an encrypted chat with you, or if I've managed to catch one of the nodes in a Tor connection, but not the others. Or maybe I control a hidden service that you're accessing. And let's assume that you're connected over Wi-Fi. So I don't actually control the data that goes over the air, but I do control the length. Well, by varying the length, I can inject that same Morse code by sending a short packet for a dit and a long packet for a da, and then varying the spacing between them. This allows me to turn your Wi-Fi connection into a loud beacon with error correction that can easily be received at a long distance. And then if I have a guess as to which city you're in, I can drive a truck around that city hoping to identify the Wi-Fi connection, especially if this is something that I can keep up for hours or for days, such as if you're a common user of the service or your host is over Wi-Fi. Now for frequency shift keying, the frequency itself rises for a 1 and is lower for a 0. This variant is called 2FSK because there are two frequencies that you're shifting between. And it's kind of like FM, except that these shifts are finite and they're quick. So it'll jump back and forth for the individual bits, and it's digital data, not audio. This is how Bluetooth works. This is how the very slowest this is how the more modern keyless entry systems for cars work. This is also how the Ant Plus and all of those wireless exercise sensors work. So suppose that we want to do packet and packet on this, but it's being filtered in software. And the filter is smart and checks to make sure that the message we're sending is not a valid packet no matter how the bits are shifted, right? Because this is 1 bit per symbol. We don't need byte alignment. We don't need nibble alignment. We could send everything like off by 2 bits, and it would still get through. So suppose the filtering software is checking for all of that. We need another loophole. So the loophole that we can use is FSK ghosting. If on channel 8 we send a given pattern, like 0, 1, 0, 1, 0, 1, on the channel above and the channel below, because of the way the filters work out, the opposite of those bits will be seen. Because as you're on the lower frequency and you receive a 1, and the legitimate frequency sends a 0, the 1 will come out in the strong frequency is just above your center. And then when the legitimate one sends a 1, you see that as a 0 because the strong frequency is so far away that your receiver sees it as the absence of a strong 1, which it will automatically calibrate to be a 0. And in this way, just by inverting all of the bits and then hoping that the receiver is on just slightly the wrong channel, you can inject a message that was never intended to be transmitted. There's also phase shift keying, where the phase of the signal is inverted. This is what Zigbee uses. So in the earlier diagram, when I showed you the 32 ones and zeros that would represent a given nibble, each 4 of those were a single symbol at QPSK. And this is also why the shifts nicely aligned into sets of 4. So this idea that a 0 is always a 0 and a 1 is always a 1 is wrong. You're actually physically affecting the environment when you send a packet. And that has physical side effects that are different from what the radio itself intended. And sometimes you can abuse these to smuggle in packets that shouldn't be there or to fingerprint the device that you're dealing with.
But more importantly, if you think about the OSI model, the picture that you have is that you receive that which has been transmitted, or you don't. So the valid frame that your radio gives you is exactly what was being sent your way by a transmitter. And this is a lie. This is a lie of gigantic proportions. In fact, as you have seen, you can receive something that has not been transmitted, not even nearly in the form that you're receiving. Just think about the implications of this for trusting your receiver and all the stack above it.
So as we hinted at before, these radios have dialects in that they have different tolerances for deviations from the standard. And by misrepresenting that standard, you can send a shorter packet, or that will only be received by certain frames. So to figure out what these dialects were and how to abuse them, we used the packet-in-packet trick. But we changed the start of frame delimiter register on the transmitter so that the transmitter would send an outer frame that was never receivable by anyone. And this allowed us to control the inner frame just by setting bytes. And this allowed us to remotely inject layer 1 with perfect success in order to figure out what sorts of abuses the receiver could handle. So this allows us to transmit towards specific devices, allowing for wireless intrusion detection system evasion. Because we can transmit to only the devices that we want to attack, while ignoring the sensor devices that are looking for these attacks. This became a project called Isotope. Sergey?
Isotope, well, as the story goes, when we met, I was trying to convince Travis to do some fingerprinting of receivers. And I count it as one of my few accomplishments that I actually managed to convince Travis, because he was like, fingerprinting, who needs that? I mean, there is a ton of work in that. People have been looking for minute differences between transmitters. Who cares? Well, it turns out that, it's almost as useless as looking at your typical elements and counting the neutrons in them. Yeah, it's the protons that matter. You got your charge. But a neutron more, a neutron less, it's still the same chemical element. Who cares? Except when it's uranium. There is this thing called uranium-235, which is an isotope of your common uranium-238. And then it catches a neutron and it produces this thing called uranium-236, and that is known as the chain reaction. And that was the beginning of the work out of which the packet-in-packet came out of, and later this entire framework for fingerprinting receivers and for making receivers see what is never sent.
So we're running short on time, so I'm going to quickly jump through our fingerprinting tricks.
We have an extra 5 minutes, though.
Okay.
Because we started late. So the Cumberland Gap. This is, neighbor, this is your...
Yeah, so the Cumberland Gap features in a number of folk songs in the region that I come from. The idea here is that we send a series of Fs before the preamble in order to confuse the receiver into becoming misaligned with a longer packet. We do this by changing the SFD that we can't take out of the transmitter, and instead we change it to something else, just so that the receiver doesn't match on it. This is sort of recreating the condition of a packet-in-packet exploit, but ensuring that it will always take effect. Because the packet-in-packet exploit is used in places in which the attacker has no radio. There's also the Franconian notch, in which we send a couple of Fs, which is part of the wrong symbol set. Remember that 0 to 7 is one set, and 8 to F is another set. We send Fs just before the starter frame delimiter in order to see whether that's matched on by the receiving radio. Some of these radios treat the end of the preamble as part of the starter frame delimiter and will refuse to receive anything if it doesn't line up. We also have another style called the Franconian bridge. So for the Franconian notch, we just take these zeros here and we replace them with Fs, or maybe more Fs, or maybe more Fs. And then we measure the responses to see how the different chips react to this. And that allows us to discriminate against particular receivers. And so we can use that to transmit just to the Raven while ensuring that the AP mote sees nothing. We call these shaped charge attacks because we can transmit packets that are only seen by a particular receiver. This is the packet capture as the Raven sees it. We can then shrink that and add how the AP mote sees it. And you'll notice that the AP mote only sees those that were sent with the full preamble, while the Raven sees it with the abusive preambles. So there is pwnage to be had in the phi layer. You can exploit things by learning mistakes in the implementation of the file layer or in the design of the file layer. For example, this packet-in-packet vulnerability is not a software mistake. It can't be patched by software. The only way to fix it is to either encrypt everything that you ever carry and that anyone around you ever carries, or to redesign the protocols in a way in which they would not be vulnerable to this.
Which actually means moving the SFD matching to the chip layer, perhaps, because as it happens, it's done on the symbol layer. And by that time, your error correction logic has already done its work, replacing your misaligned symbols with your actual ones.
But while that's part of a solution, that's not necessarily enough. For example, on wired Ethernet, there's actually an out-of-code marker for the start of frame and for the end of frame. So in theory, that should be good, because there's no way that I, as the attacker, can include a start of frame marker inside of an IP packet that I'm sending over an Ethernet network. The problem is that inside of the chip, an Ethernet card is designed, and way back when, had physically separate chips for the PHY and the MAC. So the PHY takes the incoming symbols, and it decodes them, and it puts those out on one wire. It has another wire that it is a status indicator to mark that the symbols are good and meaningful. And then it has another wire that it pulses at the beginning and the end of the packet. So what Andrea Berisani and a colleague of his discovered was that these two chips with the three wires, the wire that marks the beginning and the end of the packet is kind of redundant because you have this other wire that marks where the symbols are valid. So it turns out that in 3/4 of the Ethernet cards in the market, this MAC chip will actually only pay attention to those first two wires. It ignores the wire that marks where the start and the end are. So if you jiggle the Ethernet cable during the middle of a packet and the checksum matches up from where the wire reconnects to the end, it will allow you to do a remote frame injection in the same way that you could in radio packet-in-packet, even though the protocol itself should not suffer from this vulnerability. Because while it doesn't suffer from it at the physical layer on the Ethernet cable, it does suffer from it on the physical layer between the PHY chip and the MAC chip. So these layers of abstraction become boundaries of competence, and these boundaries of competence are where exploitable vulnerabilities are found. So I suggest that if you'd like to find some of these, you read the papers and play along. Cool. Great. Thank you kindly.